was we talked about monotone likelihood rho property, which we defined as so basic idea is to introduce a property which conveys that larger values of the statistic correspond to larger values of theta. Or in other words, larger values of theta will yield larger values of the statistic stochastically, because statistic is a random variable. So a statistic having a larger value doesn't make sense. Only you can talk about in terms of that this statistic is larger in stochastic sense. And in that context, we introduced the concept of stochastically increasing property, which was that if probability that Tx is greater than x under theta 1 is less than or equal to probability that Tx is bigger than x under theta 2. So that means if theta 1 is less than theta 2, probability that Tx takes a value larger than any threshold is smaller. For theta 1 is smaller. So so first we introduced stochastic increasing property. Yeah. You don't have to take permission, you can just walk in. Right? What it means is a statistic Tx would have a stochastic increasing property if probability under theta 1 that Tx is greater than any threshold T would be less than or equal to probability under theta 2 that Tx is greater than T for every T belonging to R. Right? What does this mean? That means whatever threshold small t you take, small t is a fixed quantity. Whatever threshold small t you take, probability that under theta 1, Tx takes larger values, larger than T, is always smaller than probability under theta 2 that Tx takes values larger than T for every theta 1 less than or equal to theta 2. If that happens, we say that the statistic Tx, which is coming from a family of distributions, has a stochastic increasing property. What was the likelihood ratio property? Now one can show that this property is equivalent to saying that if you have a stochastic increasing property in a statistic, that is equivalent to saying that expected value of psi of Tx would always be less than or equal to expected value of theta 2 psi of Tx. Right? For every theta 1 less than or equal to theta 2. And for every increasing psi. That means if you say psi is increasing, on an average, under theta 1, psi will take a smaller value than its expected value under theta 2. And that makes sense, right? Because psi is increasing, so that means larger values of psi corresponds to larger values of x, which stochastically should correspond to larger values of theta, and that is what it is saying. So as I said, try to understand what they are trying to convey rather than just writing down them as a mathematical formula. Then it will be much easier for you to appreciate these concepts. Then we talk about monotone likelihood ratio property. What it says is, I look at the densities or probability mass function, f theta 2x upon f theta 1x. Certainly, this would be a function of some statistic. It's increasing in Tx whenever theta 1 is less than or equal to theta 2. That is a monotone likelihood ratio. And one can show that if you have MLR property, that implies stochastically increasing property. Right? So MLR implies stochastically increasing property. The reason why, although MLR is a much stronger property, because MLR implies SIP, but it is easier to verify. In general, verifying stochastically increasing property means you should compare the distribution functions, right? These are 1 minus distribution functions. That may be sometimes cumbersome. So that's why we go for a stronger condition, which is easier to verify, which anyway implies this thing. Of course, some examples of stochastically increasing properties are location families, right? So stochastically increasing properties are P, which is a collection of distribution functions, let me call, and where f theta x is nothing but f of x minus theta, where f is some other. Note that there is a difference between this f theta and f. F is some other. You can write down f naught. No, there is no need to write down. Now, if this happens, f is some distribution function, right? If this happens, you know that distribution function is always increasing, right? So that means this quantity would be decreasing in theta. If this quantity is decreasing in theta, that means 1 minus of this would be increasing in theta. And what is 1 minus of this? Probability that x greater than x or tx greater than x if it is a distribution function. Another is a scale also. F of x given theta. Provided x is positive for x and 0 otherwise. 0. And also same thing, decreasing in theta. So 1 minus this would be increasing in theta, and you have this. MLR property is also possessed by a lot of distributions. In fact, any distribution you name it, it will mostly have MLR property in some statistic, either in TX or some statistics. So some examples of MLR are, but before that, I showed that if you have a stochastically increasing property, then that is equivalent to showing this result. My question is, that means if I have MLR, that would imply this, right? Because MLR implies SIP and SIP is equivalent to that. So that means MLR happens and this. So let me write down the lemma. So P is f theta, theta belonging to theta, where theta is subset of R. This is a family of PDFs having MLR in some statistic Tx. That MLR is subset Tx. That means f theta 2 upon f theta 1 is increasing in Tx, is an increasing function of Tx whenever theta 1 is less than or equal to theta 2. Now suppose psi is an increasing function, a non-decreasing function. Then expected value of psi x is increasing in theta. One can prove it very straightforward manner. Want me to prove it? Proof is not difficult. Just write it down. So let theta 1 is less than theta 2. Where theta 1 is less than theta 2. What I have to show? I have to show that E theta 2 psi x would be bigger than or equal to E theta 1 psi x. Did I complete the proof last time or not? Completed the proof. Okay. Then that anyway. So this is anyway. So this was a repetition of what we did last time. So let's consider some examples of this. So a lot of distributions belong to exponential families, right? That you know. And what we would see is all the distributions which belong to the exponential family would have MLR. And if they have MLR, that means this is what would happen. So let me consider this example. Suppose theta is a subset of R. Theta is increasing. Theta. Because just keep everything in one pocket. Yeah. And suppose eta theta is increasing in theta belonging to theta. And suppose your f theta x, that means joint density of the sample, is of the type exponential eta theta tx minus xi theta into hx. A lot of families we have seen are of this type. Has MLR in Tx. Right. So any exponential family where this eta of this type, where eta theta is an increasing function, would have MLR. Now you can see very easily f theta 2x upon f theta 1x is nothing but exponential to power xi theta 1 minus xi theta 2. Hx gets cancelled, then e to power eta theta 2 minus eta theta 1 into tx. All right. As a function of t, what is happening? Because eta was increasing function, so eta theta 2 minus eta theta 1 is greater than 0 for theta 2 greater than theta 1. Then it is e to power some positive quantity into tx. That means it is an increasing function of tx. Now note that sometimes what may happen is you may not get eta theta to be an increasing function. You may get a decreasing function of theta. Right? Then you change your statistics tx to minus tx. Then it would have MLR in minus tx, right? Rather than tx. Is that okay? So this tells you to find class of distributions which have MLR. So that means all those normal, binomial, Poisson, negative binomial, everything which you studied, most of them have MLR property. So let us consider a few examples. I will illustrate a few of them. The rest of them you can do of your own. So example, let us say x1, x2, xm are IID with PDF or PMF f theta. Right? So joint PDF of so let me call this as G theta because I was using. So f theta of x, which is x1, x2, xn, is f theta of x1, x2, xn, which is product I is equal to 1 to n g theta xi, right? So let us now consider some examples The first example where x1 has binomial m theta. Theta belongs to theta, which is 0, 1. M is known. Can you tell in what statistic it will have MLR? Summation xi or x bar. You see, first of all, that your intuition suggests that if it has MLR, it should be in x bar only. Larger value of, because theta corresponds to a population mean, right? It is m theta. So how the larger value of a population mean would get captured in the sample? Only through larger values of sample mean. So the intuition anyway suggests that it should have MLR. And we have seen anyway exponential families all have MLR. So my intuition suggests that it should have MLR in x bar only, because x bar would come into the joint PDF, right? And that you can see your f theta x is product I is equal to 1 to m choose xi. Then theta to power summation xi, 1 minus theta to power m minus summation xi. So that becomes theta upon 1 minus theta to power summation xi. I write down that in the exponential form, so it becomes e to power log of theta upon 1 minus theta into summation xi. Is that okay? I can write down this in terms of x bar also, because it will be only just multiplying by n. And then plus 1 minus theta to power n, so which is n log 1 minus theta. Can you compare with this? What is your eta? Eta theta is log of theta upon 1 minus theta. Theta upon 1 minus theta is an increasing function of theta. Log itself is an increasing function of theta. So increasing function of an increasing function is an increasing function. So it is going to be an increasing function. Is that okay? You can easily see that theta upon 1 minus theta is an increasing function. Just take the derivative, or you can write down this as 1 upon 1 by theta minus 1. 1 by theta is a decreasing, so denominator is a decreasing, so 1 upon that would become increasing. Okay, so now I think you are in a position to tell it about a lot of distributions. So let me just list a few of them so that every time when they occur in solving any of the problems, you don't have to verify they have MLR. You can always make a table and say that these are the distributions which have MLR in this and this and this. All right. Okay. X1 has Poisson theta. Theta belongs to theta, which is 0 infinity. Can you tell it has MLR in both? Again, the mean is theta, so if it has MLR, it has to be in summation xi or x bar. You see, if it has MLR in summation xi, it has MLR in x bar also, because then you can take eta theta to be n log theta upon 1 minus theta. N is a constant, positive constant, so Tx is equal to summation xi. So it has MLR in summation xi or x bar. What would be eta theta over here? Can anyone tell? Here it would come e to power minus n theta and theta to power summation xi. That would become e to power summation xi log theta. Log theta, right? Which is increasing in theta belonging to 0 infinity. And what is your Tx over here? Again, summation xi. So Poisson also has MLR in summation xi. They all belong to negative binomial R theta. R is known. So what would be this? Number of trials required to R its success. So p to power r, 1 minus p to power yeah, so it will be log something, right? You can see that this also would have MLR in what? Summation xi, right? Okay. Tx. Because actually I'm not writing down what eta theta is because negative binomial distribution has two forms. One is number of failures preceding the RS success, and the other is number of tries required to get the RS success. Eta theta would just differ by one factor, that's all. Okay. Now let's look at normal theta sigma naught square. Here also your intuition suggests that because theta is a mean, so it will have MLR in summation xi or x bar. What is the eta theta over here? It would be e to power minus 1 by 2 sigma naught square summation xi square. That doesn't involve any theta. Then e to power n theta x bar by sigma naught square. Right? E to power minus 1 by 2 summation xi square. So what would be eta theta? E to power nx bar is e to power summation xi theta by sigma naught square, right? Is that okay? That would be a thing because e to power minus 1 by 2 sigma naught square summation xi minus theta whole square. So summation xi square by sigma naught square would be hx part because it has no theta. Then minus 2 theta summation xi would be same as 2 gets cancelled from the denominator to sigma naught square, and theta by sigma naught square into summation xi, and tx is all right. Okay, now let's consider another example. X1 is normal mu naught theta square. Theta belonging to theta. Yeah, eta theta is yes, you're right. Because e to power in that exponential, the way we have written down is e to power eta theta something, right? Yeah. In this case, what would be eta theta? Mu naught is known. It is directly e to power minus 1 by 2 theta square summation xi. So what is your eta theta? Minus 1 by 2 theta square, right? Eta theta is nothing but minus 1 by 2 theta square. And what is your tx? Summation I is equal to 1 to n xi minus mu naught whole square. Is this an increasing function of theta? Because theta is positive. So it is an increasing function of theta, right? This is an increasing function of theta. So that is why it is has MLR. Now note that since now you're doing advanced level statistics courses, I would advise you that whenever you see a mathematical result, start thinking statistically about it. Unless a statistical result does not convey a statistical thinking behind it, there is a problem in your understanding somewhere. That means that result has not conveyed what it was supposed to be meant for. Now let's look at this. For example, this is a simple statement, right? That it has MLR in summation xi minus mu naught whole square. What does it convey? When I introduce the definition of MLR, I conveyed the message that basically MLR is nothing but it is conveying that larger values of statistics stochastically would amount to larger values of theta. Now here theta is a variance or a standard deviation. So they should convey, the larger values of that should be conveyed through sample in terms of a larger value of sample variance or some constant multiple of that, right? Because larger value of sample size is fixed, so larger values of sample variance is equivalent to saying that larger values of summation xi minus mu naught whole square. And that is what is happening over here. If it had to have a MLR, it cannot have a MLR in X bar. That is very clear, because larger value of a population variance, which was theta, cannot be conveyed through sample mean. It has to be some function of sample variance. Now in this case, since mu naught is known, it will be through summation xi minus mu naught whole square. Is that okay? Sixth, exponential mu naught theta. What would be eta theta over here? Anyone? This is e to the power minus summation xi minus, because mu naught is a scale location parameter, summation xi minus mu naught by theta. So that is e to the power minus summation xi by theta minus 1 by theta. And what is your Tx? Yeah. In fact, you can retain whole mu naught together. So it is summation xi minus mu naught. All right. So see, a lot of institutions are having gamma theta alpha naught. Theta is a scale parameter, right? I don't know how, what is the notation. I think I'm using this only. Is not. So what is the eta theta over here? See, density would come product xi to power alpha naught minus 1. Then e to power minus summation xi by theta, right? That is the only thing would come. So eta theta is again minus 1 by theta. Tx is summation xi. That is also intuitively makes sense, because in the gamma case, expected value is nothing but alpha naught times theta. Alpha naught is known. So larger values of theta have to, larger values of theta means larger values of sample mean, population mean, and they would be conveyed through larger values of the sample mean or equivalency summation xi, right? So these are some of the examples. You can go for more. I can write down one more. X1 is double exponential. Location parameter is theta. Scale parameter is sigma naught. Theta belongs to capital theta, which is R. Sigma naught greater than 0 is known. This doesn't belong to exponential family, right? Because it would be e to the power minus modulus of xi minus theta. So range theta will have to bracket. So, but if you interchange, then it may belong, right? So let us say mu naught and theta, right? So what would be eta theta over here? E to the power minus 1 by theta summation xi minus mu naught. So that means eta theta is nothing but minus 1 by theta. Tx would be how much in this case? Anyone? summation xi minus mu naught. Okay, so these were a lot of examples of exponential families where you have MLR property. Now let's consider some examples which do not belong to exponential family. So for example, the distributions where the support depends on the theta, right? They do not belong to exponential family. They cannot belong to exponential family. One such example is uniform zero theta, right? x1, x2, xn are IID uniform zero theta. Theta belongs to, which is 0 to infinity. What is your f theta x? Joint period. Anyone? It is 1 by theta. So 1 by theta to power n. Each xi less than theta. So that means xn less than theta. And each xi should be greater than 0, right? Which is minimum is greater than 0 basically. 0 otherwise. Let us consider for theta 2 greater than theta 1. And of course, they have to belong to the parameter space. That means both should be greater than 0, right? So for theta 2 greater than theta 1 greater than 0. F theta 2x upon f theta 1x. Okay, now let us start thinking statistically. Now here, you know that normally we will make inferences based on my complete sufficient statistic or minimal sufficient statistic. Here it would be xn. So let's start thinking statistically. These x1, x2, xn are uniformly distributed on 0 to theta. Where your xn would be? If x1, x2, xn are uniformly distributed over 0 to theta, xn would be towards which end? Near theta. All right. Now I have said I have increased theta. That means it is expected that my maximum would move towards the further right. So xn would increase. So it suggests that my intuition suggests that it should have MLR in larger values of theta only. And otherwise also you know that expected value of xn is nothing but n upon n plus 1 theta. Right? So that all is intuition. There is no proof. I'm saying your intuition suggests that it should have MLR in this thing. Now you're trying to verify that. So why not it has MLR in xn and why not in summation xi? That motivation I'm trying to give you. That even if you think statistically, forget about what is derived mathematically, you would reach at the same conclusion. So let's look at what happens over here. Now note that here everything depends on theta. So it depends on where theta 1 is, where theta 2 is, and that is what f theta 2x and f theta. So what you know is your 0 is over here, theta 1 is over here, theta 2 is over here. So first thing is, if xn, I know that each xi minimum is greater than 0, so maximum would be bigger than 0 in the sample space. So one thing is if my xn is between 0 to theta 1. If xn is between 0 to theta 1, what is f theta 2x? Yeah? 1 by theta to power n, because if xn is between 0 to theta 1, that means xn is between 0 to theta 2, that means xn is less than theta 2. If xn is less than theta 2, f theta 2x is 1 by theta 2 to power n. All right. And what is f theta 1x? because xn is also less than theta 1. So f theta 1x would be 1 by theta 1 to power n. Good. I need not bother about equality because when xn is theta 1, because probability of that is 0. Now let's look at xn greater than theta 1. If xn is greater than theta 1, what is this quantity? 1 by theta 2 power n, because xn is still less than theta 2. Because I have to see only in the support. When theta 1 and theta 2 are there, xn is between theta 1 and theta 2. So if you want xn theta 1 and theta 2. Because beyond theta 2, anyway, it is a 0 by 0 form, which doesn't make sense. Then how much is this? That means f theta 2x is still xn less than theta 2. So 1 by theta 2 power n by 0. And I've said when I'm saying it is increasing, I'm also including infinity. And something positive by 0 is nothing but. So what is this? It is constant in certain range from xn from 0 to theta 1 as a function of x, as a function of xn. And then xn, if it's between theta 1 to theta 2, it just jumps to infinity. So that means it is an increasing function of xn. So your Tx is equal to xn. That means your uniform 0 theta has MLR in the largest order statistic. Is that okay? Okay. Now that means another example which is there. ID exponential, let us say theta sigma naught, where theta belongs to theta, which is R, sigma naught greater than 0 is not. What is your f theta x? It would be e to power minus summation xi minus theta by sigma naught, right? So e to power minus summation xi by sigma naught plus n theta by sigma naught, right? If each xi is bigger than theta, that means minimum is bigger than theta. And 0 otherwise. Now here you can easily see that f theta 2x upon f theta 1x is increasing in x1. So it would have MLR in x1. So through these various examples, we saw that most of the examples, most of the distributions which we have encountered so far have MLR. Of course, there are distributions which don't have MLR in any statistic. For example, Cauchy distribution. Just take a single observation, right? Just take a single observation from x has PDF f theta x, which is 1 by pi minus theta whole square. I'm not considering a sample. Sample is much more complicated. Just try to see if you have a sample 1. Does it have MLR in any statistic? Does it have MLR, for example, in X? So let's see. So here theta can take any value in the real line. Your parameter space is the whole real line. So for theta 1 less than theta 2, f theta 2x upon f theta 1x turns out to be how much? 1 plus x minus theta 1 whole square two whole square. Now note that is what I'm saying. Your intuition may suggest something, but sometimes your intuition may be wrong. And this is one such situation. Your intuition is wrong, not that it is actually wrong, because you have not given enough thought to it why it is happening. And I'll tell you why. First, let us try to understand these are location family. Location family has SIP. So this should have SIP, that means larger values of theta should correspond to larger values of x. In terms of, if I think everything in terms of SIP, stochastically increasing, then my intuition is fine. And which happens because it is a location family. But when I look at MLR, let us try to see what is happening to MLR over here. Is it an increasing function of x? Let us look at what is happening at the two tails when x is going to plus or minus infinity. Where it is going? As x goes to plus minus infinity, it go to 1, right? Because the highest power of x square is 1. You can divide it by that, and 1 will remain, and then that should be 0. So 1 by 1, it will be. So this goes to 1 as x goes to plus minus infinity. So suddenly this itself shows that it cannot be increasing, right? Unless it is a constant. Right? Minus infinity, it is same thing, and then it comes to, when you go to plus infinity, it comes to the same thing. So it cannot be monotonic. So it doesn't have MLR. In fact, you can see at its value at theta x equal to 0 is nothing but 1 plus theta 1 square upon 1 plus theta 2 square. So it is not even constant function. So this does not have MLR. So if you're just thinking that MLR should always support larger values of theta to larger values of x, this is where your intuition gets failed. And that is very obvious if you just give a little bit serious thought. Why it is happening is because MLR is exactly not larger values of theta corresponding to larger values of x. It is the SIP which says larger values of theta should correspond to the larger values of x intuitively. MLR is a much stronger property. If MLR holds, that implies that larger values of x would correspond to larger values of theta, but not the other way. So there may be situations where larger values of x may be corresponding to the larger values of theta, but you may not have MLR. And this is one such example. Is that clear, the explanation which I gave, which beats you? Okay, so now we are in a position to derive the uniformly most powerful test in many situations. So let us consider first one-sided alternatives. Any questions in? So any questions in the discussion we had so far? Okay. Note, so UMP alpha test or one-sided alternatives. So let's consider H naught theta less than or equal to theta naught. First, let me consider only this theta greater than theta naught. These are one-sided, right? Because you're saying theta lies on the one side. Alternative, you say theta lies on the other side. So that is the reason why they are called one. So let me do this theorem. Or it could be theta greater than less than or equal to theta naught and alternative theta less than theta naught. Any of these hypotheses. So suppose X has a PDF f theta. This could be PDF or PMF, which belongs to a family P. Let me say call this as a distribution G, which belongs to the family f theta. Theta belongs to 1 by theta. So these are one parameter family of distributions. So theta is a subset of R. There is only theta, the unknown, there is only one unknown parameter, that is what case it covers. And suppose this has MLR in Tx. And I'm interested in estimating, testing theta less than or equal to theta naught against theta greater than theta naught. I'm saying forget about the theorem statement. You should be in a position to tell me what should be the, if there is a uniformly most powerful test, what should be the form of the uniformly most powerful test? Yes, just use your statistical mind. It has MLR. MLR means larger values of thetas should get reflected in the larger values of T. Your alternative says, under alternative, theta is large, right? Theta bigger than theta naught. So that means larger values of theta are falling under alternative hypothesis. And since my family has MLR in Tx, that should get reflected in the sample through larger values of T. So if H1 is true, that should get reflected in the data, because you see, finally I have to make decision based on my data. So how do I judge from the data whether there is evidence of H1 being true or H0 being true? I see H1 would be true if theta is large. And since T has MLR, that would get reflected through larger values of T. So can you tell what would be the uniformly most powerful test if there is one? Reject if T greater than C, and so on, right? Now in this case, under alternative, you have smaller values of theta. So here you reject for smaller values. So your test would be just complementary or dual of that test. So let me stop over here because I don't think I can even complete a statement today. So let's start from here next time. And we'll see that a lot of situations dealing with one-sided hypothesis testing problems would be covered through this. So you're all normal, exponential, all those examples which I wrote down, geometric and so on. So you can always get a uniformly most powerful test through this theorem. Okay.